This is the first video of logistic regression using R. Here we illustrate the differences between logistic regression and linear regression with an example. This lists the age in year AGE and presence or absence of evidence of significant coronary heart disease CHD for 100 subjects in a hypothetical study of risk factors for heart disease. The table also contains an identifier variable ID. This is identifier variable ID and an age group AGEGRP. The outcome variable is CHD, which is coded with a value of 0 to indicate that CHD is absent, or 1 to indicate that it is present in the individual. Now we explore the relationship between AGE and the presence or absence of CHD in this group. For this, we draw scatter diagram between AGE and CHD. For scatter diagram, we use plot function and this is the scatter diagram. In this scatter diagram, we see that all points fall on one of two parallel lines representing the presence of CHD or absence of CHD. We observe that there is some tendency for the individuals with no evidence of CHD to be younger than those with evidence of CHD. So, it does not provide a clear picture of the nature of the relationship between CHD and AGE. AGE. The main problem with this figure is that the variability in CHD at all ages is large. This makes it difficult to see any functional relationship between AGE and CHD. One common method of removing some variation is to create intervals for independent variable and compute the mean of the outcome variable within each group. So now we construct table using following code. So this is a frequency table. First row correspond to interval, second is a frequency. Now we construct another table using following code. This table contains age group, frequency, present absence and mean. This is the code. So first column is interval, second is frequency, third is present, fourth absent in that group, and fifth is a mean of present in that group. Here we see that as age increases, the proportion of individuals with evidence of CHD increases. So this one is age group, second is frequency, then present in that group, absent in that group, mean of present. Then we observe that if you look at first and fifth column, then we see that as age group increases, then mean also increases. Now we draw a diagram where line diagram where x-axis is a age group and y-axis is a mean. Then this is the diagram. This plot provides considerable insight into the relationship between CHD and age in this study. So here we see that as age increases, age group increases, CHD also increases. The plot in this figure is similar to what one might obtain if the same process of grouping and averaging were performed in a linear regression. We note two important differences. The first difference concerns the nature of the relationship between the outcome and independent variables. For linear modalities, expectation y given x equal to beta naught plus beta 1x And this is possible when expectation y given x takes any value y given x takes any values as x ranges between minus infinity to plus infinity. Minus infinity to plus infinity. But for dichotomous variable, this should be 0 to 1. Sorry, this should be 0 to 1. 0 to 1. Sorry, this is not minus 1, this is 0. So this should be 0 to 1. In addition, the plot shows that this mean approaches 0 and 1 gradually. The change in the expectation y given x per unit change in x becomes progressively smaller as the conditional mean gets closer to 0 to 1. The curve is said to be S-shaped and resembles a plot of the cumulative distribution of a continuous random variable. Thus, it should not seem surprising that some well-known cumulative distributions have been used to provide a model for expectation y given x in the case when y is dichotomous. The model we use is based on the logistic distribution. Many distribution functions have been proposed for use in the analysis of dichotomous outcome variable. There are two primary reasons for choosing the logistic distribution. First, from the mathematical point of view, it is extremely flexible and easily used function. Second, it is model parameter provide it is model parameter provides the basis for clinically meaningful estimates of effect. Here we compare the value of deviance. So first we feed this model using GLM function. This is the inbuilt function GLM. So we get the summary of this fitting. We use this. Then for ANOVA table we use ANOV within bracket fit. For confidence interval we use confit. First we run this GLM function, then summary output. This is the summary output. So this is the output. Here we compare the value of deviance with and without the independent variable. So first one is intercept, second one is edge, then null deviance, then residual deviance. So null deviance means without independent variables, and deviance with independent variables means residual deviance. So G equal to D within bracket model without the variable and G is a measure which implies the change in deviance due to the inclusion of independent variable in the model. So G equal to D within bracket model without the variable minus D, and here D model without the variable is 36.66, then G equal to D model without the variable minus D model with the variable, where model with the variable model with variable and it is 107.35. So G equal to 29.31. Now we compute p value. Since G follows under H naught chi squared with 1 degrees of freedom, then the p value is probability chi square greater than 29.31 given chi square follow chi squared with 1 degrees of freedom. We can compute p value using R code, that is 1 minus p chi square within bracket 29.31 comma 1, then enter. Then we see that p value is very small, which is less than 0.001. Thus we have convincing evidence that age is a significant variable in predicting CHD. So this implies we have convincing evidence that convincing evidence that age is a significant variable in predicting significant variable in predicting CHD. The result suggests that now we see that the estimate corresponding age is 0.111 approximately. So this result suggests that the change in the log odds of CHD per 1 year increase in age is 0.111. So Now we construct confidence interval of this change by using the code. The code is this. This is the output. So you see that corresponding age, the 95% confidence interval of this change is approximately 0.067 and 0.162. This means this could be as little as 0.067 or as much as 0.162 with 95% confidence. Now we see that the constant or intercept provides an estimate of the log odds ratio of CHD at 0 years of age. As a result, the constant term by itself has no useful clinical interpretation. Now, using this code, we get this exponent. For confidence interval of this exponent, we use this code. For prediction, we use this code. For residual, we use this code. So these are all codes you can use. This is the first video of logistic regression in R. Please stay with us. We will upload second video. Till then, thank you.